Hello, this is Lourens van Niekerk representing the Stellenbosch University Mathematics Society from South Africa. So my favorite number is tree 3, which it doesn't look like a number, but it represents a number and it represents a very, very big number. And the reason I chose this number is because when I found out about the hashtag MegaFavNumbers, I thought about a number which I heard about 8 years ago in a general mathematics book. I think it was called Maths 1001. And they just said that it was big, and I had no idea how big it was. I didn't even know what it was. And I believe still no one knows just how big it really is. But let me explain what this number actually is. So tree 3 actually represents a game. So the game goes like this. If, say, we were to choose tree 1, that would mean that we would play a game where you make nodes and then you make trees thereafter. So this would be the first tree, and this would be a second one, then you get a third, and so on. And the rule is that each node, or each tree, needs to have at most the amount of nodes as the tree which it is. So this node must have this tree must have 2 nodes at max. This one can have 2 as well. It doesn't need to have 3, it can even have 1, and so on. But the rule is that the 1 means that you can only use 1 color, and the other rule is that the game ends once one of the previous trees can be fit inside one of the following trees. So if we were to look here, tree 1, we're only using 1 color. First one needs to be 1. Second tree, we can fit the first tree in there because that is the first tree, and the game ends. So we know that tree 1 is equal to 1 because we could only make 1 tree without the game failing. Then when we look at tree 2, now we're allowed to use 2 nodes, 2 colors for the nodes. So let's say we start with green again. So the first one is green, and then the second one, let's say we make red, and we have it like that. We could also have made it 1 red node instead of 2, but let's just make it 2, and say third one we can make 1, it doesn't need to be 3. This tree doesn't fit inside there, and this one's a different color. But now we would find that if we now try and make a 4th tree, if we start with green, the first tree can fit in the 4th one, and if we start with red, the 3rd tree can fit in there. So the 4th one is not possible. So now we know that tree 2 is equal to 3. Just to note that the number here, the 1 and the 3, represents the maximum amount of trees that you could play in this game. Not any specific number inside it, just the maximum number. So this is where tree 3 comes in, because it's not small. It gets big very, very, very fast. Like, it's not just over the million, it's over an inconceivable amount of size. It is extremely big, and maybe you would wonder how do we know that it's finite and not infinite? Is because there was a mathematician called Kruskal who proved that for all of the trees, all of them will be finite, though we can't think of how big it would be. So let's just play a small game of tree 3. So say we start with green again, our first tree is this. Then say we start our second one with red, there. Then the third one, say we make that blue and 2 reds. Fourth one, we can make blue with just 1 red. And you can see it doesn't follow in itself. This one doesn't fit in that and that. And we can continue like this, and you'd think this game ends much faster than it is, but it is actually a huge number. And I'm not sure about this, I read this somewhere, but from what I understood is if you take plank time, which is the amount of time it takes for light to travel 1 Planck distance, which is the smallest distance we can conceive of in physics, that's going to be a very, very, very nano time scale that we're working on. If we were to draw 1 tree using the tree 3 game, if we were to draw 1 tree every Planck time, that is about, that equates towards about 1 with 44 zeros behind it per second. That many trees per second. If we were to play this game at that speed, the universe would end before we have finished all of the trees for the maximum amount that this game can allow. That is how big this number is. And I love it because mathematics, not just being magical and mystical at some points, it's the most magical for me when you can't even conceive of it for how big it is. Another example would be when people talk about the amount of combinations that exist for a Rubik's Cube, how many different situations there are. But tree 3 is much bigger. It is bigger than Graham's number, I believe, as well. So this has been my MegaFav number, and I hope you enjoyed it. Thank you.